Hi everyone. Today we're going to learn how to use Wireshark. We're going to learn a little bit of nice things about how Wireshark can help with network traffic analysis, and the reason why is because it's got a lot of features and a lot of integration, and you can do a lot of things, to be honest. But in this lab we're just going to focus on how to use a Wireshark and how to perform simple analysis of the Wireshark logs that we see. So as you can see, this is the application. It has a graphical user interface, and you can capture any of the network interfaces, and that's what it does. So it basically sits on top of any of the network interface that is specified and performs a passive scan of everything that is incoming or outgoing within that interface. And in this case, we're going to use ETH0, which is the Ethernet adapter for the virtual Ethernet adapter for this virtual machine. Before we start the scan, which is this fin button, I'm going to show you how we can generate some kind of traffic, right? So we use Nmap for this, and one of the most popular command is the SN, which is a ping command. And this IP address range is basically a local IP address range for most of the home networks. So what we're going to do is scan this IP address range and try to see what kind of network devices are visible and available within this network. Before I press enter, I'm going to start this scan, and then I'm going to press this. And you can clearly see in the background that we're generating a lot of traffic. Well, the SYN scan, or a regular ping scan, what it does is that it initially does a ping, ICMP ping request, and then if the device is available, performs a TCP scan. Just to understand more about what the device is, and you can see here that it scanned the 256 IP addresses, which had 9 hosts, in about less than 30 seconds. That's how long it took. So clearly you can see that there are name of the devices and associated IP addresses, local IP addresses associated with it, and here you can see my phone as well, right? What we're going to do is we're going to stop this, and we're going to try to understand what this traffic is doing. So a very interesting feature and a very widely used feature is the right click anywhere. Well, if you go to protocol and click right on top of protocol or right on top of destination, you can specify that as apply as filter. And what it does is that it takes that column and takes the value of that particular log and sets it so that we can only see the ICMP logs here. We can do the same for source or destination IP addresses. This makes it much more easier to troubleshoot or try to identify a bunch of packets that might be clustered together. But our objective here is to understand what the initial scanning did in the network. So basically, when it scanned the first 256 IP address ranges, it started with 1.1 all the way to 2, 9, 10. And here you can see the first reply. So how ICMP requests or ping requests work is that it sends a bunch of requests to all the IP addresses, and as long as it receives a reply, which means that there is a device that is active and available associated with that IP address, it gives that information back to the host machine that is requesting the scan and confirms that there is a device that's present. So first was 1.1, so that was the first device that we picked up, and here you can see this is the name of the device, and here's the IP address for it. And after that we went ahead scanning furthermore, reached 44, and they got another reply. So here you can see 44 actually is a Mac laptop within that network, right? Furthermore, we have a few more responses, right? This is where you got 115, so another device that's somewhere here. Maybe we skipped these two, but that's all right. What we can do now is we can take this as an example and see what happened here. So IP source was this. We can remove that and directly say IP source as this, and then what we can do is IP destination bias filter or selected as this. What it does is that destination, every time the destination was this, gives the response. But what we're looking for here is that or IP destination could be the same as 1.115. So here you can see that this is how a request and reply were sent, right? So there's other types of traffic. You can see some TCP traffic here running on these IP address ranges. You can see, so what we can do is we can apply this as a filter and select this, and we can see from the start that here you can see for 239, and probably there's a device at 239, yes. But what we're looking for here is that applies a filter selected, and maybe, or wait, applies a filter or selected, and then 115. That was the previous device that we were looking for, right? So here, this is ICMP. Let's make this and end. Okay, so yeah, it didn't send a TCP to 115, which is interesting, but yeah, this is how you troubleshoot or analyze network traffic within Wireshark. Okay, so this one was unencrypted traffic, so it was pretty easy for us to kind of get this packets and try to understand it. Well, what about encrypted traffic? That's an interesting question. So again, Wireshark can capture any packets, either it's encrypted or unencrypted. The question is, what can it do with the encrypted traffic? And the answer to that is pretty straightforward. If it has access to the keys, the encryption keys associated with it, it can decrypt it and be able to see or view those packets. If not, it will show everything is encrypted, and we might want to wait until quantum cryptography becomes a regular thing to be able to decrypt it, right? A lot of attackers these days are, harvest now and decrypt it later. And that's especially the case for all these asymmetric encryptions that are being performed, or less stronger encryption, deprecated encryption ciphers that are out there still in use. But anyways, what we're going to do now as part of the lab, we're going to stop this. And before I stop it, I just want to show one last thing, that you can actually save these traffic packets into into files, and that it can be repurposed or reused, or it can be part of some kind of forensic analysis. Okay, so we're going to now capture traffic that could be encrypted, and for that we need some traffic generated in an encrypted format. We're going to go through a website, and an encrypted website, and see what kind of logs does Wireshark generate. But before that, we need to do specifically one thing, which is so there is this export feature which enables registering of SSL key log into a file. And what it does is that so here you can see that the file hasn't yet been created, and we're going to just touch this and see if now you can see here that the SSL key log is now created. What the SSL key log registers all the encryption keys that was used, and we're going to now start. So we're going to start a Ethernet capture again, and we're going to just push this, and we're going to use Chromium. For some reason I tried Firefox, and due to some technical difficulties it wasn't able to decrypt the files using the SSL keylog, but for this purpose of the lab we're going to use Chromium, which is an available browser within a lot of virtual machines, or it's very easy to install anyways, but we're going to use this. And you can clearly see the traffic generation has already started, but we're going to just open a website so that it generates more traffic. Once it does, to the point where we think we have enough traffic, I think we can stop this and close the browser. I think that's, yeah, that's no longer needed. But you can see here, you can see address resolution protocol, which is basically, you know, protocol used for defining what the local IP address for that you know, device is. So yeah, it just, you know, it's doing a lookup here. You can see, you know, asking for OS 192.168.72.4, and you know, response from ARP, some DNS, some quick logs here, some couple of TCP logs, and this is where I think the first TLS encryption. Right. So we have TLS 1.3 used here. Well, basically transport layer security 1.2 or 1.3 are industry standards that are utilized for encryption of traffic that is exchanged over HTTPS layer. It's, in other words, it's basically a set of approved cipher algorithms or cryptographic algorithms that that perform encryption on the traffic in transit. So we can see here TLS 1. Well, TLS 1.2 actually uses both symmetric and asymmetric encryption algorithm. The initial exchange to, you know, securely share the key is performed using asymmetric encryption, something like RSA or epileptic curves, and then it uses a shared secret key to perform encryption further, so that more traffic can be more efficiently or faster be sent across the network. So here you can see that transport layer security is available, 1.3 specifically. You can see some of the cipher suits that are approved. Here you can see all of these are the approved list of approved cipher suits in TLS 1.3, and in this is industry approved, so all of these are highly secure. Once we have client hello, we also have something like server hello right here. So in server hello, I think this is where we confirm the encryption cipher suit that will be in use, which is TLS advanced encryption algorithm standard 128. That's the size of the key. AS 128 is fairly secure. It's a symmetric algorithm, encryption algorithm, and this is the key that will be used to share, exchange the remaining of the data after the initial pairing. Okay, so after this, what we can do is that we just have a bunch of data that is encrypted, and you can see that by, you can see here when a lot of TCP packets are shared, it says, well, instead of saying what the packets are about, it just gives a bunch of application data, because we can see what's outside of it. We can see what has been used to kind of encapsulate these data that's within it, but we don't have the access or the ability to view the data inside of it because because it's in encrypted state. So here you can see, here you can see this portion of the packet is actually encrypted data, so we don't know what's in it. You just see a bunch of random strings, right? This is where we have our SSL key, and what we're going to do is we're just going to check if the SSL key.log has some kind of data, and it does. So it has a bunch of secret keys that were used for the exchange of information within the browser. And what we're going to do is we're going to go to edit and preferences, and then we're going to specify the protocol, which is going to be TLS, and then we're going to select this, which has already been done before, so I'm just going to hit apply. And once I hit apply, not sure if I did this correctly, but if I hit apply, it should have changed the encryption data to encrypted data to unencrypted format. But we can verify this by saying we can see what kind of HTTP data is there. Yes, it did encrypted to. Yes, we can see HTTP2 data, which wasn't visible before we used the keys, and clearly we probably also have HTTP3 data, which is further encapsulated using a shared secret, but at least we're able to get till here to be able to see HTTP3 and 2 and regular HTTP data. And basically decrypting this means we get to see all kinds of data that were exchanged. For example, here you can see some of the headers, some settings, some kind of data here, JSON data, which you can see, and yeah, you can see further information here. And these are still encrypted using AES 128, so we're not able to see the information here, but because the key was exchanged after the initial pairing. But what we achieved here was that we were able to decrypt the outer layer of the RSA encryption algorithm, or ECC, whichever one was used, and be able to view the traffic within it, and gives us a better idea of what kind of traffic was being exchanged through this. So this is it. This is the lab for Wireshark. It's a very powerful tool, and we just touched the tip of the iceberg. And well, I think this is enough for this lab, but we will continue having more detailed labs in the future if thank you.